support in the non-negative reals, right? So this is the formula for the expected value of xj, and we obtain this general formula for the expected value of xj in terms of the claims rate and the conditional distribution, because this expected value, this conditional expected value, is calculated through this conditional distribution function. Okay, and any questions so far? Everything clear? If not, please do not hesitate in raising your hand or asking directly. Yes. Anyone? I thought somebody was going to ask something. Okay, anytime you can interrupt me, no problem. Okay, and the last thing we wrote was this example. Of course, we are going to be working on it today. And we said we will consider a 1-year term life insurance policy with a certain insured amount of CJ. Remember, J is just a number, could be a policy number that identifies a particular client. Okay, so J is the number of the client. Whatever, right? And and that will depend, of course, on the client's age, sex, and if he's or she's a smoker or non-smoker. Okay, but we also said that we will consider additional coverage, right? It's not just that if the person dies, we pay CJ. It says the payment of twice the insured amount in case of accidental death. Okay, so the basic insured amount is CJ, but in the particular case, the death, the cause of death is an accident, then we multiply by 2 CJ. Okay, so how many outcomes do we have in terms of payments? What are the possible scenarios for this policy in terms of premiums?
CJ and double CJ.
And you are missing one more.
And 0?
And 0, right? 0 is always a possibility. Remember that the claims random variable is total claims from policy J during the period of the policy, right? Could be 0. In fact, that's the one that has the highest probability. Remember the graph? This is a typical graph. This big jump, remember the size of the jump at 0 is the probability that there is no claim. And we said usually this probability is going to be very high, the probability of 0, because we just cover or sell products for insurance to cover events that have a very low probability. Probably a huge financial impact in a person's life, but with a very low probability. So that's why 0 always has a very high probability, a lot closer to 1 than to 0. Okay, so never forget. So the possible values in terms of claims is 0, CJ, or 2 times CJ. Okay, but also I'm just considering this one additional coverage, but in practice there could be many other additional coverages, right? So and this is open to creativity, right? Because people that sell insurance, they are always thinking what else, what kind of additional coverage they can include in the policy to make it more attractive. Okay, and so any additional coverage will have an impact in the model in order to price to calculate the premium that has to be charged to the client. Okay, so in this case it's very simple, just one additional coverage, but you may consider or propose or come up with ideas of more additional coverages, right? So now, so it says consider a probability of death in an accident, kappa J. okay? Because person dies, some people die because of an illness, some others die because of an accident. Just for you to know, usually the probability of dying from an illness is a lot higher than dying from an accident. The probability of dying in an accident is quite small in comparison to non-accidental deaths, okay? Just for you to know. So the task was to calculate the expected value of xj and to obtain the non-conditional distribution function of xj. Basically, is to apply these formulas, right? And this proposition 4 to calculate the expected value. In fact, we can calculate it in two ways. This proposition is telling us that it's very easy to calculate the expected value of xj through this formula, but we can do it directly with the probability distribution of xj. We will do it in two ways, okay? So this is the example. Any questions about what we have to do? We are going to do it right now, but any questions about the statements, what is involved in this particular insurance product? Is it clear for everyone? If not, please raise your hand or raise your voice, no problem. Okay, well, let me start sharing a Blackboard, just a moment. Oh, sorry. Sorry. Okay. Now, I will start sharing, just a moment. Okay. Some things. No. I'm doing something wrong. Just a moment. Oops. I know what's going on. Let me see. Because I modified some configuration. Let me see. Okay. So can you see that I'm writing in the Blackboard? Yes? No?
Yeah.
Yes? Okay.
Yes.
Perfect. Okay. Sorry about that. And let me just... Okay. Okay. So we are going with number 5, which is the example. Okay. So we said 1 year term. 1 year term life insurance policy. So insured amount. We said CJ, mortality rate, it's not it, it's just probability, sorry, QJ, and additional coverage, we said twice insured amount if accidental death, okay? And we said we will consider a probability of death in case of accident. It's going to be value kappa j, in 0, 1. Of course, this mortality rate is also in 0, 1. How would you think this probability is calculated in practice? We already discussed about the mortality rate, but what about this one? How do you think?
Historical data?
How?
With historical data?
That's right, but how? What kind of data? Imagine that you're working in an insurance company, a new insurance company, and they are starting to model this product, and they say, okay, tell us what you need to estimate this probability. What kind of information you will ask for?
We would focus more in the deaths that happen because of the accidents.
In fact, all the deaths, and which proportion of all deaths are because of an accident, right? It's just going to be the proportion of deaths that were because of an accident from all deaths will give you an empirical estimation, right, of the probability of dying in an accident. So this probability is going to be conditional, right? I mean, considering the information, that's why I'm asking, how would you imagine this is going to be estimated in practice? You will say, okay, from all historical deaths that we have recorded from our clients, which proportion of all deaths were because of an accident? So it's going to be, what's going to be the probability of an accident given death? And this is very important in practice. I think I already mentioned that in practice, almost all information is conditional on something, right? So usually, that's why this is very common in risk theory, that you will calculate non-conditional things in terms of conditional things. Why? Because in practice, all the data, all the information comes in a conditional way. Okay, so is it clear for everyone that this kappa J is in fact a conditional probability given death? I mean, because from all deaths, we will identify which ones were because of an accident. And then we will use the proportion of accidents in terms of all deaths as an estimation of this probability of death in case of accident, right? Is it clear for everyone?
Yes.
Okay, good. And so we said we want to obtain the expected value of xj and the non-conditional distribution function of f of xj. Okay, so remember the formulas that we need to calculate the conditional distribution, right? So in the case of qj, we already have it. It's here, but for this part, right? We need the conditional distribution of xj given xj positive, right? So we need the conditional distribution of xj given the conditional one, right? Of xj given xj positive, right? First of all, so okay, let me go to the new page. So first of all, the first thing you should ask about a random variable that you are trying to obtain or approximate is what's the range, right? What's the set of possible values of that random variable? In this case, I'm asking about the range of xj given that xj is positive. So what are the possible values in this case?
CJ and 2 times CJ.
okay, and no 0, right? Because it's given that it's positive. So conditioning on the fact that xj is positive, then we forget about 0 momentarily, and there are only two possibilities. There is a positive claim, either it's CJ, non-accidental death, or 2 times CJ, accidental death, okay? And so, what about kappa J? I mean, these are the two possible values of xj given xj positive. So clearly, this is, what type of random variable is this one? From the 3 types we know, what kind of random
Discrete.
variable? Discrete, right? Only 2 possible values, okay? 2 positive possible values. So this is not a Bernoulli, okay? But it's kind of a Bernoulli because of the 2 possible values, but strictly speaking, it's not 0, 1, it's CJ or 2 times CJ, okay? So we just need to know the probability of one of these values, and the other one will be the complement, right? So let's take, for example, this case, when the random variable is equal to CJ, the conditional case, right? So what is going to be the probability of xj being equal to 2 times CJ, given that xj is positive?
KJ.
Kappa j, okay, yes, I know, I mean, this Greek letter looks like letter K, so yes, KJ or kappa j, okay. Okay, kappa j, right? So by complement, the probability of xj being equal to cj, the other possible value, given that xj is positive has to be 1 minus kappa j, okay? So now we can calculate immediately. I mean, we don't need to obtain explicitly the probability distribution of non-conditional probability of xj. We can use formula 4 or proposition 4, and remember, let me go. So we are going to use this proposition. So we are going to calculate first the expected value of xj, the non-conditional one. We already know qj, so let's just calculate this conditional expectation, which is very easy because now we have the probability distribution of xj given xj positive. We just did that, right? It's just here. Only 2 probability mass points. This is the probability of this one, and 1 minus kappa j is the probability of this value. So if we want to calculate the conditional expectation of xj given xj positive, so this is going to be equal to what? Remember, it's just each possible value times its probability, right? And the sum, okay? So we just have to add each possible value multiplied by its probability. So in this case, we have CJ multiplied by this value and 2 times CJ multiplied by this value, right? So this is going to be just,
I
yes?
have a question
Yes.
in that sense because I don't catch if we have to think about those events like disjoint events, because if they aren't disjoint events, then we can't add them and multiply them by the probability the usual way. So I didn't understand very well that.
Okay. I mean, let me see if I understand your question or your concern. What we have here, I mean, this conditional probability has only 2 possible values. So that makes this a discrete random variable. Just think about a random variable that takes 2 possible values. And from the information we have, from this product, we know the probability of this happening, given that there is a positive claim. This conditioning event, that means that the person died. I don't know from which cause. But XJ being positive, that means since it's a life insurance product, the only possibility that XJ is positive is because the person died within the policy period. Okay? So XJ conditioning on XJ positive is given that the person died, either the person died because of an accident or it was a non-accident, right? If it was because of an accident, we have to pay 2 times CJ. So this is the probability. This is information given by the problem. And by complement, the probability of the other possible value has to be 1 minus kappa j. So the way you calculate this expected value, since it's a discrete random variable, I mean, the general formula is the sum of all possible values of x, okay, of x times the probability of xj equal x given xj positive, right? This is the general definition for the expected value in terms of the probability mass function. In this case, we have a probability mass function given here, right? Given by these 2 possible values, and we have the probabilities. So this is the general formula for the expected value. Now, in this case, x only has 2 possible values. So again, what was your question here?
Oh no, I was confused in the interpretation because the first time I tried to solve the problem, I didn't saw the kappa j as
A
as
conditional,
a probability
a conditional probability.
as a conditional probability. So I got confused in
Okay.
that. But
Yeah, no, I understand.
no, it's all clear. Thank you.
Okay, good. But it's very important. That's what I mentioned, that the tricky part here was interpretation. Remember that I told you that the probability knowledge that we need to understand risk theory models is quite basic. So don't expect very sophisticated probability models here. The important part, the tricky part in risk theory is interpretation of concepts, of probabilities, to understand this tricky situation that in practice, information probabilities estimated from historical data are usually, almost in all cases, think about it or remember, usually it's going to be a conditional probability or conditional information on something, right? So now here, so as we said, the possible values are Cj multiplied by its probability, so it's going to be 1 minus kappa j that multiplies the value Cj plus kappa j multiplying the other possible value that is 2 times Cj, right? And then we can just rearrange this in a different way. We can just make the multiplication, distribute. So it's Cj minus kappa j times Cj plus 2 kappa j Cj. And we can just write this as well, here, well, this one cancels one of these. So we have Cj plus kappa j Cj. So we get 1 plus kappa j times Cj, okay? So this is the conditional expectation of xj given xj positive. But we want the non-conditional one, right? So the interesting thing here is that without having to obtain explicitly the probability distribution, the non-conditional probability distribution of xj, we can calculate its expected value, right? So then, by proposition 4, I think somebody's asking something, probably. Oh, yes, go ahead.
Yes,
Yes.
Mr. Professor, why we cannot put the probability of xj equal to cj equal to, well, given that xj is positive, equal to qj? I didn't understand that thing.
Okay. Well, okay, because this is a conditional probability. I mean, QJ is a probability that a person dies, no matter the cause. So when you use QJ, you can estimate how many, for example, if you apply QJ to a certain number of people, you will get the probability of people dying, but without considering the cause of death. Okay? But if given death, you want to know if a person died because of an accident or not, I mean, here, QJ doesn't take part in this calculation because it's given that the person died, okay? With which probability this person died? With probability QJ, but this already happened here. That's why it's out of the scene here, right? Because this already happened. We know that the probability of XJ, I mean, to say it in this way, the probability of XJ being positive is QJ. That is QJ. That's the probability of death. But here we don't distinguish the cause. Because the person dies, okay, probability of the person dies is QJ. That is QJ. But here we have a different question. We're saying, given that the person died, what's the probability that it was because of an accident? Is it clear now? What is QJ?
Yes, Professor, thanks.
Perfect. You're welcome. Okay. So then, since we have this formula for the conditional expectation of xj given that the person died, that's what this event represents. Given that the person died, what's the expected value of xj? So here, by proposition 4, remember we have this very simple formula, sorry, here, this one. It's just QJ times the conditional expectation we just calculated, right? So by proposition 4, we get that the expected value, the non-conditional one of xj, is just qj times the expected value of xj given xj positive, right? And we just replace this, right? And we get 1 plus kappa j times qj times cj, right? Okay? So, first task, check, right? Done. Any questions so far? But this is just to calculate the non-conditional expectation of xj, right? We look that this formula involves both probabilities, right? The probability of death is here, represented by qj, by all causes, and the adjustment of kappa j is here, right? The adjustment of 1 plus kappa j is considering this possibility of dying because of an accident, or not. It could be, right? So on average, on the long run average, this is going to be the expected value of xj. Now, we are going to go further because this is just to calculate the expected value of xj. So it was enough to know the conditional expectation. But if we want to make more calculations about xj, in addition to just its expected value, then we need to obtain the general formula for its distribution function. Okay? The distribution function, the non-conditional distribution function of xj. Okay? So in that case, we are going to apply formula 3, right? Okay, well, this was formula 3. This is in the notes from the previous class. This is formula, that was formula 3. Okay? So this is the one that we are going to obtain. But first of all, we need to obtain the conditional distribution of xj, and then we use this formula, right? But we don't have it, but we can obtain it very, very easily with the information we already have. Because we already have here these two probabilities represent the probability mass function, right? So it's straightforward to obtain a step function, the cumulative distribution function, the CDF, of the conditional distribution of xj given xj positive. Okay, so let's do that. Okay, so let's now apply formula 3 to obtain the distribution function of the claims random variable. Okay, first of all, since we already have the PMF, remember PMF, probability mass function of xj given xj positive. Remember that Cj has probability of xj being equal to Cj equal, sorry, the conditional one, given that xj is positive equals 1 minus kappa j, and the probability of xj, the other possibility is that equals 2 times Cj given xj positive equals kappa j, right? So since we have the PMF, it's straightforward to obtain the CDF, right? So then the CDF f of xj given xj positive equals, by definition, the probability of xj being less or equal than small x given xj positive, right? And this is for every x in the reals. Remember that the domain of any CDF is the whole real line, right? So, but of course, this is going to be a step function because it comes from a discrete random variable model, right? So how is this going to behave? We can sketch a graph of it very easily because it's only two possible values. So we will have just two jumps, right? Because for a discrete random variable, the CDF is step functions that has jumps or discontinuities at the probability mass point. And we just have two probability mass points here for the conditional one, right? So let's just write here 0, small x. So let's say, well, here we have 1, which is the maximum value for a CDF, of course. Yeah. Okay. And let's say here we have CJ. And so approximately 2 CJ is going to be here. Okay. So let's draw some lines here. Let's say here, here. And also we need kappa J. As I told you, kappa J is the proportion, the proportion of people from all the people that die, which proportion was because of an accident. And I already told you that usually it's a very small proportion of it. So kappa J is usually going to be closer to 0 than to 1. So 1 minus kappa J is going to be closer to 1 than to 0, of course, right? So since the probability, the first jump is going to be at CJ because CJ is less than 2 times CJ. So the first jump is going to be of size 1 minus kappa J, right? So we have to identify here a value 1 minus kappa J. It says here 1 minus kappa J. Okay. And then now we can draw our step function here, which is going to be something like this. Yeah. And then we have a first jump exactly at CJ, and it's going to be a jump of size 1 minus kappa J, right? And then we have a second jump at 2 times CJ. And of course, the size of this jump is going to be kappa J, right? Because it's the probability of 2 times CJ, right? So we have that last jump. And then we have probability 1 from here to infinity, right? Yeah. Yeah, because it's right continuous, of course. Here. And here, right? So does everyone agree that this is a sketch, a valid sketch of the graph of the CDF of the conditional distribution of xj given xj positive? Is it clear for everyone?
Yes.
Yes.
Good? Perfect.
I have
Okay.
a new question,
Yes.
but I think it's more like in general, not just for the example.
Yes, yes.
Always we have like the claim amount, like the 2CJ, that it's the, how to do I say it? The more money could get the insurance client,
Mm-hmm.
always going to touch 1 when we touch the maximum amount.
Do you mean about the distribution function or?
Yes, in the distribution function.
Oh, well, yes, because for example, imagine that you consider additional coverages that imply 3 or 4 different values, right? Because it say, well, normal death, non-accidental, is going to pay the insurance amount, which is CJ. Then we may have, okay, in case of accidental death, it's going to be twice the insured amount. That is what we have here. And then you may have a third additional coverage. We say, okay, but if the accidental death was because of a plane crash, okay, because it's very, very strange to die in a plane crash. But if in addition to that, we say, okay, from all accidental deaths, what's the proportion of all accidental deaths that happened because the plane the person was traveling crashed, right? So then you will have, and in that case, you may say, okay, in that case, we offer to pay your family 3 times or 10 times the insurance amount, okay? So yes, in that case, we will have a third jump, and then that will be all the cases, because when you accumulate for all the cases, of course, you have probability 1. Yes, is it clear?
Yes.
Okay, good. But this is, I mean, the interesting thing about insurance product is that this is open to creativity. And it's insurance companies have different areas. They have what they call the technical area, where reserves are calculated and the solvency capital requirement is calculated. But they also have a products area, which is different from the technical area, but they also have actuaries there. And that area is quite interesting because it's more creative and people are kind of thinking about ideas for new products or how to add interesting coverages, additional coverages to existing insurance products, okay? But of course, it's interesting because sometimes people from the products area say, okay, we have a new idea about a new coverage that we have to add to our products. They explain their idea, but then the actuaries in the technical area have to model that, right? So, okay, they have to modify the existing model and gather whatever information they need to calculate the additional probabilities, because each additional coverage will have certain probability associated to something. And there are going to be also some other conditional probabilities that have to be taken into account. Okay? So this is a very simplified version, but please think that you may consider more than one additional coverage, okay? And you will have more possible values for the claims, okay? Not just CJ or 2CJ, it could be 3CJ or certain other rule that you may come up with, okay? Good. So now we have this formula. Well, we sketched the graph, right? But of course, from this graph, we can easily get our formula. We can just write down, let's say, that the explicit formula, and we should consider lucky in this case that we can obtain explicit formulas, okay? For very simple products, especially for insurance, for life insurance, it's quite common to have explicit formulas, right? But for non-life insurance, okay, property and casualty, car insurance, liability insurance, right? Usually you don't have an explicit formula for the distribution functions involved. Usually you have to approximate them through stochastic simulation that we will discuss about it very, very soon. By the way, don't forget, oh, that's very important. Let me go back here. Remember that you have all this, right? So I'm assuming that you are spending some extra time reviewing these 8 items here about Julia programming. That is not just about the basics about Julia programming, but also some probabilistic calculations with Julia, including simulation of random variables, stochastic optimization with Julia. Now that I mentioned that we are going to need these tools, because right now we are dealing with very simple models from which we can obtain explicit formulas. And that's nice to understand, to analyze things. But Later, that's not going to be possible anymore, and then we will have to approximate those distribution functions we are interested in through stochastic simulation. Okay, so please don't forget to spend some time making sure that you understand all this, and also remember that since time ago I shared this value of risk. It's a video which does not cover everything in the article, right? So, well, you're supposed to check the video and read the article, okay? And I want to spend time for questions on Friday, okay? So this Friday, please bring your questions about either Julia programming or about this video and this article, okay? Because it's going to be already 2 weeks from the semester. So I think it's kind of enough for you, at least to let me know if you have questions about these tools in Julia programming and about this article, which is very, very important, okay? So please don't forget to do that. But now we can still play in the ground where we can obtain explicit formulas, okay? So the explicit formula that we just sketched in the graph, but it was obtained from the conditional probability mass function. So it's going to be 1 minus kappa j times this indicator function, right? Plus the indicator function of x being greater or equal than 2CJ, right? Because if x, remember, x is any real number. So to the left of CJ, this indicator function becomes 0. This one, of course, 0. So this equals 0, okay? Which is this part, okay? If we evaluate this distribution function in a value of x that is greater or equal than CJ and strictly less than 2 times CJ, then we have this step part of the function, right? So in this case, this indicator function becomes 1, and the value is 1 minus kappa j, this one, right? And this indicator function equals 0. And in case x is greater or equal to 2CJ, this indicator function becomes 0, and this one becomes a number 1. Okay, so we take this value, right? Okay, so I think it's clear, the formula. If not, please let me know. Okay, so we have this one, so then we can apply this formula, right? Well, I think it was from this lecture, formula 3, just for you to know that, be sure that it was formula 3, right? This one, right? Because 2j is given, it's part of the information we have for the problem, and we just got xj, given xj positive, okay? By the way, what is tau? Remember what is tau in general and in this particular case? But the concept, the policy limit. Good, the policy limit. And in this case, what's the policy limit?
2 times CJ.
CJ, okay. In this case, the policy limit is 2 times CJ in this particular case. Okay, good. So we just have to replace this formula we just had here in here. Okay, so I'm not going to do all the algebra. I mean, that's for you to do all the details. So I'm just going to mention that you have to do that. So then we replace the formula of f of xj, the conditional, in formula 3, right? With tau equal 2 times Cj, okay? And we obtain, and we get, please do the details, okay? Just do the algebra and make sure that you arrive to the following formula. And we get f of xj is going to be 1 minus qj times the indicator function of x being greater or equal than 0, less than Cj, plus 1 minus Qj kappa j times the indicator function of Cj being less than equal than x, less than 2 times Cj, plus the indicator function of, well, that's the advantage of this kind of infinite blackboard, right? Okay, and plus the indicator function of x being greater or equal than 2Cj. Okay, so now we can sketch a graph of this, right? So this is the non-conditional one. And let's sketch a quick graph of it. Yeah. And we will have 0, Cj, 2 times Cj. Now, remember, we are, for the non-conditional one, we have 3 possible values, right? So here we expect to have probability mass over 0, Cj, and 2 times Cj, okay? Because it's the non-conditional one. Here, let's say we have 1. And here, okay. And here we have 3 jumps, right? This first jump, 1 minus qj, and then we have a second jump, which goes to 1 minus qj, but qj is multiplied by kappa j. So this product is smaller than qj, right? So 1 minus qj kappa j is a greater quantity than this one, okay? So let's assume that here we have, let's say, qj, and then here we have 1 minus qj kappa j, okay? So the graph is going to be this way. So before 0, we have nothing, okay? So it's probability 0. So to the left of 0, oh, sorry, we have 0. Then, exactly at 0, we have a jump of size 1 minus qj, right? Nothing happened. The person survived, okay? So we pay 0, right? So we have here this jump. But then,
Teacher,
yes,
I have a doubt.
yes,
The last line we draw here, I think it may be called 1 minus QJ.
yes, sorry, yes. You're right. Thank you very much. Here, yes, you're right. Let me put this closer. 1, yes, thank you very much. It was 1 minus qj, okay? And then, here we go. And here, continuity from the right. Then we have the first jump in case of non-accidental death, okay? And so here we get this point here. And goes here this way. And then a second jump, 2 times kappa j, and the last jump. Okay. Sorry, forgot to put this here. X. And let me check the previous graphs because I think I forgot. Oh no, yes, it's X there. Okay, yeah, everything is in place. Okay, so okay, good. So here we have 3 probability mass points, right? So from this formula, then we can get the PMF of XA, right? Because we already know that the non-conditional version of XJ, that's the range, sorry, the range of XJ, non-conditional, the claims random variable, it may claim 0, CJ, or 2 times CJ, right? So it's a discrete random variable also. And since we already obtained its joint distribution function, its CDF, sorry, then we can get the probability mass function from here, right? I mean, the probability of 0 is the size of this jump. The probability, the non-conditional probability of CJ is the size of this jump. And the non-conditional probability of 2 times CJ is the size of this jump, whatever it is, right? So we can get it from there and say, okay, let's make a table for possible values of X, and then we calculate the probability of Xj being equal to X, right? Where X can take the values 0, CJ, and 2 times CJ, right? So let's make a table here. Right. So in the first case, the probability of 0 is the size of the jump, no surprises, 1 minus qj, right? As expected, we would say. 1 minus qj. But the non-conditional probability of cj is the size of this jump, right? And the size of that jump is 1. Let me write it here. It's going to be 1, no, this side. It's going to be 1 minus qj kappa j minus 1 minus qj, right? minus
It is Qj minus Qj kappa j.
Qj, one, yes, that's right. Because we cancel these ones, right? And then we get Qj minus times minus is plus Qj minus Qj, right? So this equals, sorry, this equals Qj times 1 minus kappa j, right? So here in the table, we write just Qj times 1 minus kappa j, okay? And the last one can be calculated either by complement, right? 1 minus the sum of these two, right? Or just calculate this difference, right? 1 minus, it's very clear here, right? 1 minus this, the ones cancel, then we get Qj times kappa j, right? Very fast. So the last one is Qj kappa j, okay? So do you see the difference here? Because first we got the conditional PMF of xj given xj positive, right? Which was only two possible values. Here, this is the PMF, this is the probability of Cj and 2 times of Cj, kappa j and 1 minus kappa j. But the non-conditional one, which includes the value 0, has different values. For example, here for 2 times Cj, we have kappa j, but here, that same value is Qj times kappa j, okay, because it's the non-conditional version, okay? And from here, so we have the explicit PMF of non-conditional xj. Without using formula from proposition number 4, we can immediately calculate, right, the expected value of xj, right? Which is by definition the sum of all the possible values of x multiplied by its probabilities, which is going to be 0 times 1 minus Qj, right? Plus, sorry, here, this is multiplication, right? Plus Cj, Qj times 1 minus kappa j, its probability, plus 2Cj, Qj kappa j, okay? And then you can do the algebra, right? And arrive to the conclusion that we already arrived using formula 4, right? I mean, here we are skipping using formula 4. We obtain directly the probability mass function of xj, and then we apply the definition of expected value, and we get Cj times Qj times 1 plus kappa j, right? And then add the comment as expected, because we already got that formula directly. So if you just need the expected value of xj, you don't need to do all this, right? But if you are going to make some other calculations rather than just the expected value of xj, then you have to do all the things we have done to obtain the non-conditional, to obtain the conditional distribution of xj given xj positive, and then use it in formula 3 to obtain the non-conditional CDF of xj. And in this case, since it happened to be a discrete random variable, from this one, from the jumps, we can easily obtain the PMF, the non-conditional PMF of xj, and then apply the definition of expected value. Okay? Any questions so far? And in fact, this is kind of an example of many other examples. I mean, we cannot just spend a lot of time with all the different kinds of products. The idea of this example is for you to have a general idea how to obtain, to propose a model, a claims random variable model, okay, for a certain insurance product. Of course, we chose the easiest one, okay, but of course there can be more complicated products that involve some continuous payments, especially in non-life, okay, where the claim amount can be one among a lot of uncountable possible different quantities, okay, in case of claims, non-life. Okay. Anyway, any questions so far? So that's the first idea, to have a claims random variable for each policy in a portfolio. But we said that insurance companies organize all the products they sell by portfolios, okay? What's portfolio? Just a set or a collection of individual insurance policies that have something in common. That feature in common could be that they are the same product. Well, we may have even insurance portfolio of all life insurance products. We may have an insurance portfolio of all car insurance products, okay? But sometimes certain policies are grouped by some other criteria. Probably this, you may group all the insurance policies that are sold for a certain company, right? Or for a certain organization, right? This is the portfolio of all life insurance policies from UNAM teachers, for example. Okay, this is a portfolio of all the major medical insurance for UNAM teachers. Okay, and so on. But now we started first policy by policy. How can we model them? So this is just an example, but with this you have the idea how can you do this with some other products. But now insurance companies want to deal with portfolios. Why? Because there's a very important principle in insurance that I suppose you learned from your basic course or one of your two basic courses of insurance, which is the mutuality principle, right? That the idea of insurance is that we are going to have a large number of people interested in buying the same coverage. They want coverage against an event that has a small probability, but a huge financial impact for those who suffer the consequences of that small probability event, okay? So the mutuality principle, what is behind the mutuality principle is the law of large numbers in probability, right? Because if we use the expected value, we're saying, when we say that QJ is a mortality rate, we're saying that among many people of the same characteristics, QJ is a proportion of those people that are going to die, for example, or that a proportion of people that are going to have an accident, right? So, but for that value to be useful in calculations, we need to spread these risks among many people so that we have a huge portfolio of people where just a very small part of it are going to file a claim, which implies a payment, right? So from the insurance company point of view, we need to aggregate somehow each individual risk that is part of our insurance portfolio, okay? So that's what we are going to discuss about aggregation of individual risks. So let me go for this concept. 6. Aggregation of individual. Oh, sorry. I lost my pen. Where is it? Sorry. Aggregation of individual risks. So in this case, if we consider a portfolio of n individual insurance policies. Okay? To each one, we associate a claims random variable, right? A claims random variable, as we discussed, okay? So let's assume, okay, we have a model. But in fact, we may have a general model if it's the same kind of product, as we said, life insurance with an additional coverage of 2 times the insured amount in case of death, okay? But each policy may have different mortality rate because each client has a different age, sex, and smoker, no smoker condition, right? So each QJ might be different, okay? And about the insured amount, the client chooses the insured amount, okay? So each CJ, the value CJ is going to be different, okay? So if we consider a portfolio of any individual insurance policies, we are considering a collection, right? So this portfolio is going to be a collection or a set of n random variables, right? But not necessarily independent and not necessarily identically distributed, right? So this is kind of bad news because we learn a lot of statistical procedures based on the fact that we have n IID random variables, right? Independent and identically distributed random variables. Yes, life, in terms of calculations, life becomes very easy if they are independent and identically distributed. And if they are not identically distributed, calculations do not become very difficult. The difficult part becomes when they are not independent, okay? So if they are independent but not identically distributed, it's a piece of cake. No problem. It's very easy, even in that case. But if you don't have independence, then things become quite complicated, right? Okay, so when are they or they are not independent or identically distributed? I mean, the fact that they are identically distributed is going to be quite strange in practice, right? Because each client has different characteristics, right? Even if it's the same insurance product, as the life insurance product we described in the example, of course, each client will have different age, different sex, different smoker, no smoker status, okay? So they are never going to be identically distributed, okay? But about independence, that's a thing, right? If all the people that we are considering in an insurance portfolio work in different places, they do not know each other, or whatever. I mean, that you have information about, because insurance companies know or should know how each portfolio was created, right? What's the history of that portfolio? Okay, where do the clients come from? Okay, so if there are clients from everywhere that work in different places, that live in different places, in that case, you may say, okay, the independence assumption is reasonable. Okay, and careful, I'm saying reasonable, because it's very easy in classroom, in the blackboard, to say, let this n random variables be independent, identical distributed, okay? So we are deciding that, or we are assuming that. But in practice, every time you make an assumption, you should be very, very careful, okay? And ask yourself, is this a reasonable assumption? Because it's not going to be usually possible to be 100% sure that your assumption is correct. Very often you will find yourself making assumptions. Of course, you will try to make reasonable assumptions. But when you say, I'm going to make this assumption, I think it's a reasonable assumption, you are saying, I'm not 100% sure about it. I mean, I'm pretty sure this is a good assumption, okay? But you are not completely sure. So in making assumptions, you will have to do that in practice, but you should always leave the door open to think about it. To always question, is this assumption right? I mean, sometimes you may think, oh yes, of course, all these policies can be assumed independent, but you should always question that and say, how do you know that? Have you checked where they live, where they work? Or in a certain portfolio, they might be that 10% of the portfolio are people that work in the same place. So probably you should take that group of people out of the portfolio so that you just live in the portfolio independent policies and model them as independent, and give a different treatment to those random variables, to those policies that is not reasonable to assume independence, and take that into account, okay? So those are very, very important things in practice. So when we talk about aggregation of the portfolio, so this is the part we want to deal with, aggregation. What do we mean about aggregation? Basically, we are talking about a transformation of the portfolio. What is the purpose of this transformation? So in this case, you will consider this portfolio of n claims random variables as a random vector, right? And you want to apply an aggregation function, okay? The most common one, okay, but not the only one. The most common case is when that aggregation function, because aggregation sounds like the sum, right? So it's just a sum. There are other ways to aggregate that I'm not going to discuss now, but yes, the most usual aggregation function is the sum, the simple sum, right? So we will calculate the sum of n random variables, okay? Why the sum? Because we want, the insurance company wants to know from a certain portfolio what will be the total claims that are going to be paid for that portfolio, right? How much from the whole portfolio? So it's just the sum of each of the individual claims. Remember that most of these random variables are going to have a claim value of 0, right? Just is a small proportion of these random variables will be equal to something positive, equal to the insured amount or twice the insured amount or whatever it's specified in the insurance product, okay? So what for? Because we need to know, we want to make calculations, probabilistic calculations about the portfolio, okay? We want to do, so the question is what for? What for? Well, we need the distribution function of S so that we can calculate its expected value, of course, or the median, right? Or the variance, in case it's useful to do that. Or you want to calculate the probability that S goes beyond certain amount, right? The value at risk, remember that you are studying this concept in the video and the article, okay? So the calculations in insurance company are done by portfolio, okay? So we need a point estimation of the total claims that may come up from a certain portfolio. Or what's the probability that the total claims of a certain portfolio go beyond certain amount, especially if it's a large amount that the insurance company is not well prepared to handle, right? So probably the insurance company knows that if the total claims, because they have a very bad year, and that may happen sometimes, probably the insurance company knows that if total claims go beyond this amount, they will have liquidity problems, okay? So they may want to calculate, okay, in the worst case scenario, what's the probability that the total claims from this portfolio go beyond this amount, okay? And if this probability is very, very small, they will say, okay, let's take the risk, right? If this probability is pretty high, they should do something about it, okay? So the thing is, we need the distribution function of S to make all kinds of calculations. In fact, if we want to calculate the expected value of S, we don't need this one, right? That's the good thing about the expected value. Because of the linearity property of the expected value of the sum is the sum of the individual expected values, right? So if you already have a model for each of these random variables, the expected value of the sum is just the sum of the individual expected values, no problem. But for any other calculation, for the median, for the variance, for these probabilities, for the var, you need to obtain the distribution function of S, okay? And I hope that from your experience from previous courses, you know that if the random variables are independent, identically distributed, or even just independent, it could be manageable to obtain a formula for the distribution function of S, right? But when they are not independent, just to obtain the distribution of S is going to be complicated. Usually, it is not possible to obtain an explicit formula for f of S. So in those cases, you need to approximate the distribution function of S. How? Through stochastic simulation. That's why it's very important for you to review all the material I already shared about Julia programming and stochastic simulation, because we are going to use it in some cases to approximate the distribution function of S, okay? And once you have a good approximation of the distribution function of S, you use that approximation to approximate all these quantities that are of interest, right? Okay? So if x1 to xn are not independent, we need its joint distribution, right? Joint distribution. That is x1 up to xn needs a joint distribution function, right? But portfolios, insurance portfolios are huge in practice. 1,000, 10,000. Imagine dealing with a 1,000 dimensional random vector or a 10,000 dimension random vector. Crazy, right? How are we going to deal with this? We need stochastic simulation. Okay? So only the expected value of S does not require f of S thanks to the linearity property, right? And that takes us to proposition 7. So, proposition. And instead of writing the proposition and writing the same as the proof, I will do it in the same line, right? It's so straightforward. The expected value of S is the expected value of the sum of the random variables, which is the sum of the individual expectations of the xj claims random variables. And then here we apply formula 4, right? That's why we got a general formula for the non-conditional expected value of xj, which is going to be qj times the conditional expectation of xj given xj positive. So, okay? And that's it. But what about the variance? Here we get into trouble. Because the variance does not have a linearity property, right? I mean, the variance, as I hope you remember, yes, is the sum of the individual variances, right? The sum of the individual variances plus, and here it comes the complicated part, right? 2 times the sum of a lot of covariances, right? All the possible covariances by different pairs of random variables in the portfolio. So it's the sum of all the values a, I, and j, right? Between 1 and n times the covariance. I hope you remember these formulas from your statistics courses. Okay. And how do we calculate these ones, right? Because each of these covariances, each of these, how do you calculate them? Equals the expected value of xi, xj minus the expected value of xi times the expected value of xj, right? These ones, no problem, right? From f of xj, from the marginal models, right? The same for these ones, right? The variances and the individual expectations of each random variable, no problem, because we are assuming that we already have individual risk models, okay, for each random variable. But what about this? This one, this calculation, so the problem here is that this one requires the joint distribution of the random vector xi, xj, right? For all I and j in 1 to n, with I strictly less than j, right? How many models we need here? That is how many bivariate models we need here. Just to calculate the variance, right? So just for you to think how complicated this can be, right? For the expected value, no problem. If you already have, we already obtained a general formula for the CDF of each random variable for the xj's, that's the individual risk model, no problem. We can use it to calculate the expected value or the variance, no problem. But to calculate the variance of S, we just found out that the individual models are not enough. The covariances that we have to calculate a lot of them. How many terms we have here? How many terms?
And factorial?
No. How many terms we have in this double sum? How many terms?
And square?
No. No, because I cannot be equal to j. I mean, it would be n squared. I mean, okay, that's a good point. It will be n squared. This is the same as calculating why is that? Why this formula is also correct. Probably you remember this one, where you have the sum of the individual variances plus 2 times, okay. But this one is also correct. What's going on here?
I remember that it's because when they have the same index number, it becomes the variance?
That's right, because in this double sum, we are allowing, in some cases, for I and j to be the same, right? It will depend, because I will take values freely from 1 to n, j from 1 to n, okay? Sometimes I and j will be the same, sometimes not, okay? In fact, there are only n cases, so we have n squared terms, right? So here we have n squared terms. Because somebody said n squared, well, no. Here we have n squared terms, okay? N of them have I equal to j, right? And in that case, the covariance of xi with xi, in fact, is the variance of xi, right? So there are n squared minus n, which is the same n times n minus 1 terms with I different from j, right? And that we
Yes.
will have, yes? Was somebody going to ask something? Okay. So we have n times n minus 1. But we have repeated values, right? Because the covariance of xi and xj is the same as the covariance of xj and xi. The order doesn't matter, right? But these two terms, xi and xj and xj and xi, are part of this sum and are part of these terms, right? So there is no need to sum twice these terms if you know that. That's why you have these two here, right? If you always choose I to be less than j, you will consider only half of all the covariances, but the other half have the same values. That's why you can constrain these, right? To I being strictly less than j, and then you multiply by 2. So here, if all these terms, including this multiplication by 2, need to be n times n minus 1 terms, but now we are just considering half of them. Of course, here, the answer to my question is n times n minus 1 divided by 2 terms. And that makes sense, right? Because here, I was going to say, that is the combinations of n choosing 2, right? Because we are saying, we are considering all the pairs of numbers, doesn't matter the order. I'm going to choose 2 different elements from this set from 1 to n. So how many different pairs? Well, no, not pairs, because in the pairs you have some order. No. How many different subsets of size 2 we can get out of these n elements? That's the combinations of n choosing 2, right? And that's the number of terms we have here. But this is equal to n factorial times 2 factorial times n minus 2 factorial. And then here we cancel things and we have n times n minus 1 divided by 2, right? Which is exactly what we were expecting, okay? But the comment here is that the complicated situation here is that we need this amount of different joint distributions by pairs, okay? Of course, if it's correct to assume independence, here, I mean, the message is this one. Here it doesn't matter if the xi's are independent or not independent. It doesn't make a difference for the expected value. It's always true that the expected value of the sum is the sum of the expected values. Okay? In both cases, either if the xj's are or they are not independent. But for the variance, since we have this formula, again, if the independence assumption is correct, or at least reasonable, if they are independent, what is the covariance? If you have independent random variables, what are the covariances equal to?
0.
0, right?
0.
Not the other way around, right? Remember that. Covariance equal to 0 does not imply independence. Okay? But independence implies covariance is equal to 0. So yes, in case here, for this formula, you don't need independence. But for the variance, if they are independent, the variance is also the sum of the individual variances, right? But if they are not independent, you have to calculate these covariances. And this implies to know, to have information from this amount of bivariate distributions, okay? That is bivariate distributions. So imagine that you have a portfolio of 1,000 policies or 10,000 policies in a portfolio. N equal 10,000. It's going to be crazy, right? How many different bivariate models you will need to estimate? Crazy, right? So let's just leave it there and say, okay, so in case it is reasonable to assume that x1 to xn are independent, I don't need them to be identically distributed, but independent. Independent, sorry. And let me stress that. Careful with this assumption. Okay? So you really need to have very good reasons to believe that they are independent, because usually you won't have information to prove it. Okay? Sometimes you may perform, if you have enough historical data, you may perform some statistical procedures to check if the independence assumption is reasonable or not. But it's usually a difficult task, okay? So in case it's reasonable to assume that the variables are independent, then, okay, yes, it's very easy to calculate the variance of the sum, because it's just the sum of, well, in that case, the covariance of xa, xi, xj, xi, xj is going to be equal 0 for every I different from j, right? Because when they are equal to the variance. And then, yes, in that case, the variance is just the sum of the individual variances. Okay? So, two important messages in terms of calculating things about a sum of random variables. If you are just calculating its expected value, you don't have to worry about the fact if they are or they are not independent. It doesn't matter. By in the linearity property of the expected value of the sum is always the sum of the expected value. As soon as they exist, of course, remember, right? That right? Okay. But for the variance, careful. If they are independent, things remain easy as just adding the individual variances. But if they are not independent, or you are not sure, you have to calculate these covariances, and this implies estimating a lot of different bivariate distributions. Okay? And that's just in terms of variance, right? We said that we're interested in calculating many other things, the median, or this kind of probabilities, or the value at risk of a certain level alpha of the portfolio. In those cases, you need to obtain the distribution function of S. And to obtain the distribution function of S, again, if they are independent, it's kind of easy through stochastic simulation. But if they are not independent, then this is going to become a little bit more complicated. Okay? Any questions so far? Everything okay? Okay, so as a final proposition, and this is for you to prove as homework. I will add this to the homework. Proposition. If the covariances of its I xj equals 0 for every I different from j, then the variance of S equals the sum from 1 to n of qj. Remember the qj's, right? The mortality, not the claims rate, could be mortality rate or some kind of other rate, times 1 minus qj times the conditional expected value of xj given xj positive squared plus the conditional variance of xj given xj positive. Okay? Right? Look, does this assumption imply that the random variables are independent?
No.
No, of course not, right? So, in fact, what we said is, sorry, this one, well, I will change the order of the page. This one was going to the end. Sorry. So, we said that the problem here is it's enough to assume that the covariances are equal to 0. In fact, you don't need independence. Of course, if the random variables are independent, automatically the covariances are all equal to 0, right? But the thing is that the problem is is to calculate the covariances. So it's enough to assume that the covariances are equal to 0 and you get rid of this, right? So what I'm saying here is that if all the covariances are equal to 0, okay, then you get rid of this part, sorry. You get rid of this part, but then you still have to calculate these individual variances, okay? So in fact, the homework is to calculate the variance of xj through the general formula for the claims random variable, right? We already have a formula for the expected value of xj, right? The non-conditional one, proposition 4. Now it's your job, your task, your homework to calculate the variance of xj. Because the rest is just the sum, right? It's just the sum. So this part, in fact, is just the formula. Let me write it down. This is the variance of each of xj. So what you have to prove is that the variance of xj is this. Okay? So the proof is left as homework. Okay? So I will add, and you will have to apply conditional expectation and conditional variance properties. Remember that at the beginning of the course, I said very important results from probability that we are going to need in this course is to deal with mixed type random variables and to apply conditional expectation properties. Remember the conditional expectation random variable, the conditional variance random variable. So you have to apply that to obtain, to get to this result, okay? So I will add this exercise to the homework. And is there any final question? Everything okay?
No.
No?
Everything's fine.
Perfect. Okay, it's about time. So thanks for your attention and see you next Thursday. Bye-bye.
Goodbye.
Bye.
Thank
See
you.
you. See you. Bye-bye.
Thank you.
See you.